Okay, so now I'll talk about the stability and index of self-shrinkers. So to get an intuitive sense of the stability of self-shrinkers, we can remember what happened with curve shortening flow. So the idea is we perturbed a circle, even a lot, and we got a curve that was very much not round anymore. And then we applied curve shortening flow, and it returned back to a circular shape as it shrinks. For mean curvature flow, well, we saw that it's not quite the same thing, but if we start with a round sphere and we perturb it a little, so maybe we turn it into a golf ball by adding dimples, or we stretch it out and turn it into a football shape, or whatever sport you like, you turn that round sphere into the shape of the ball for that sport, and then you apply mean curvature flow, it's going to return to being round as it shrinks. Now, certainly if we perturb it a lot, we might have the example of that dumbbell shape that we saw in that video that I showed, where it will not return to being round as it shrinks. But for small perturbations of the round sphere, if we apply mean curvature flow to that perturbed surface, it's going to return back to the round sphere. So that doesn't happen with the Angenent torus, and in fact our intuition for the Angenent torus, for why it exists, explains why. So the Angenent torus is, in some sense, just the right shape so that its meridian circles and longitude circles collapse at the exact same rate, causing it to shrink by dilations. If we perturb it, then generally speaking, it will either the meridian will collapse first or the longitude will collapse first. It won't. They won't collapse at the same rate, and so we'll no longer get an Angenent torus singularity. Okay, so if it's unstable, one question we can ask is how unstable is it? And one way to quantify instability is to ask whether it's stable for say a one-parameter family or a two-parameter family. So for example, with the Angenent torus, as in the intuition that I gave, we saw that there was a one-parameter family going from the hula hoop to the fat torus, and we expect that in between there should be a surface that will get an Angenent torus singularity. And we perhaps might guess that if we perturb this family, then still maybe not, maybe the member of the family that gets the Angenent torus singularity will change, but there will still be an Angenent singularity appearing somewhere among that family of initial conditions for mean curvature flow. So is that true or not? That's sort of a question for the index, and maybe as a spoiler, I can say that it actually is true if our perturbations are rotationally symmetric, and not true if our perturbations are allowed to not be rotationally symmetric. All right, so let's discuss index. So unstable perturbations of a self-shrinker will decrease the F functional. And so essentially we're doing something that is just the index from Morse theory, the index of a critical point. So if you're not familiar with that, I can do a very quick introduction. So you can think about critical points as being perhaps a mountaintop, where it's flat, but if you move in any of the two-dimensional space of directions, you will end up going downhill. In contrast, you can have a saddle point, or the bottom of a ridge, or the top of a valley, and it's again flat there, so it's a critical point. But there's only a one-dimensional space you can move in to go downwards. You have to go down the valley. If you go the other way, you'll end up going up the ridge. And finally, we have a crater. So there, it's once again flat, and that's stable. And there is now a zero-dimensional space of ways you can go to decrease the F functional. So the dimension of this space of directions you can go to decrease your functional, that is the Morse index of the critical point. And so that's what we're looking to understand here in the case of self-shrinkers, which are critical points for the F functional. What is the index of that critical point? So I'm going to give some toy examples illustrating stability. So here we want to think of the length functional of curves on a sphere. And of course, we know that to minimize length on a sphere, we draw a geodesic between 2 points. And so this situation is a critical point. So if I have a rubber band, if the blue curve is a rubber band, it's going to stay put. But also if I perturb this rubber band, the length will increase, and it will, if I run curve shortening flow, or just imagine it as a rubber band, it's going to return back to this shape. In contrast, we could have a very inefficient way of getting between these two cities. So this is once again a geodesic. So if we have a rubber band that's exactly in the right place joining these cities, that rubber band will stay put. So that makes it a critical point. On the other hand, it's definitely an unstable critical point. If I perturb it by moving this curve a little bit northwards, then the length will decrease. And if I run curve shortening flow, the curve will flow all the way around the sphere and eventually end up with this length minimizing geodesic here. Now I'm going to do a toy example illustrating index. So once again, we're going to look at the length functional for curves on a sphere, and we're going to look at this critical point here. So this is a geodesic. It's a critical point. If I have a rubber band here, it won't move. If I move that rubber band a little northwards, however, its length becomes shorter, and if I allow curve shortening flow to run, or intuitively I think of that rubber band as trying to decrease its length, then this rubber band will pop off the North Pole. It will shrink and shrink, move northwards, and eventually disappear at the North Pole. If I vary the curve this way, however, I'm just rotating it, then we get a situation where the red curve is also a geodesic, so it's going to stay put. And if we look at higher modes, so this particular variation of the equator is balanced north and south, and so if first of all, you can observe that its length is larger. Second of all, you can observe that if we run curve shortening flow, because it's so balanced north and south, it will return back to the equator as that rubber band tries to shrink. And certainly if we have more complicated higher modes, then once again the rubber band will return to the equator. So what we see here is that we had one unstable variation, which was this one, where the length decreased and it will move away from the equator. And then all the other ones were, this one is stable but not asymptotically stable, and these ones are all stable. So the length increases as we do this variation, and under curve shortening flow will return back to the equator. Okay, so how might we compute the index of the Angenent torus? Well, the general idea is the same one I discussed, which is that instead of having a surface, which is a member of an infinite dimensional space of surfaces, we somehow discretize. So maybe we triangulate the surface, so now we have a lot of vertices on the surface, and we sort of interpolate between the vertices with something piecewise linear. The f functional is still defined on these piecewise linear surfaces, and so now we're just back into a high-dimensional calculus setting where we have a functional on a large finite-dimensional space. We find the critical points of this functional to find where the self-shrinkers are, and to find the index, we just compute the Hessian at that critical point, and we look at the number of negative eigenvalues of this matrix. I'm going to say a little bit more about what has been known previously about the index of the Angenent torus. So one thing is that every self-shrinker actually has several unstable variations that are trivial in some way. So these are dilation and translation. And the one way to think about this is that the f functional is designed with, the weight is centered around the origin, and it has a particular scale. So it's designed with the origin in mind and 1 unit of time in mind, in the sense that it's designed to get us self-shrinkers that shrink to the origin in 1 unit of time. Now what happens if I take a self-shrinker and I dilate it to make it smaller? Well, then it's still going to shrink to the origin, but it will shrink too soon. It will shrink in less time. And if I dilate it to make it larger, then it will shrink and it will get to the origin in more time. Likewise, if I translate it, well, now it'll still shrink in 1 unit of time, but it'll shrink to the wrong place. And intuitively, one might think that well, if we zoom in at the origin, but our surface is actually shrinking towards a point near the origin, then eventually, if we zoom in on the origin, our surface will just go off to infinity, similar to how if you're in Google Maps and you want to zoom in on something and you accidentally zoom in on something nearby, the place you're actually interested in is going to fly off the screen. Okay, but there are at least three other non-trivial variations, non-trivial unstable variations of the Angenent torus. So this was proved by Liu. And I'll discuss that a little bit because that method has implications also for the numerics. So the idea is to exploit rotational symmetry. One of the reasons we're doing this work for the Angenent torus is that the Angenent torus is rotationally symmetric, and this gives us a very easy starting point for answering these questions about entropy and index. And so, as I discussed, I had the picture of the torus and the picture of its cross-section. The torus is determined by its cross-section, and so we can understand the torus just by understanding that curve. And so if we vary the cross-section, we will get a variation of the torus. However, if we just do that, we're only getting rotationally symmetric variations of the torus, and of course there are variations of the torus that are not rotationally symmetric. So dilation and vertical translation are examples of rotationally symmetric variations of the torus that we can get simply by having variations of the cross-section. But we can actually do a Fourier decomposition, so we can have more general variations that are not rotationally symmetric, and we can write them still as variations of the cross-section multiplied by a sinusoid. And so horizontal translation is an example of this. So horizontal translation is not a rotationally symmetric variation, but it can be written as u cosine theta or u sine theta. So the way Liu's work proof works is he shows that, because there are these trivial variations of dilations and vertical translation in k equals 0 and horizontal translation in k equals 1, that there actually must exist other variations in those Fourier modes with lower eigenvalues. And so how does this apply for the numerics? Well, again, we do the same thing. We look at each Fourier component individually, and within that Fourier component, we look at variations of this discrete cross-section, and we see which ones will decrease the f functional. So let's talk about the results. Okay. So here is a chart showing all of the unstable variations of the Angenent torus. So I'm going to discuss what everything here means. So first of all, the columns are k equals 0, k equals 1, k equals 2, corresponding to the Fourier modes. So k equals 0 are the rotationally symmetric variations. In here, hopefully you can see my cursor, you can find dilation here. So this is the Angenent torus, that's just smaller. And here it's vertical translation. You, of course, in this chart doesn't really let you see that this torus has been translated upwards, but this is the Angenent torus that has been translated upwards. In the k equals 1 column, we have the two horizontal translations here. Okay, so then we have these three variations here that are non-trivial, and those are the ones that Liu showed exists. This one should be fairly familiar to us. This is the variation that, at least in this picture, makes the meridian circle fatter, and if we vary it in the other direction, it would make the meridian thinner. So this is that variation we talked about. That is an unstable variation of the Angenent torus. These two are very interesting. So Liu's proof just shows that these eigenvalues have to be smaller than -1/2, but it turns out that they are actually, well, numerically speaking, they were actually very close to -1, and it turns out that they actually are -1. So that was somehow a surprising result here, that these eigenvalues are actually integers. And then finally, here we have variations with k is equal to 2. So these are our new variations that had not previously been proved to exist, and so we were able to compute them. If we go off to k equals 3 and further, then all of the eigenvalues are positive, so there are no further variations here. So the eigenvalues increase as we increase k, and intuitively that makes sense, because if you make your surface more and more wobbly, then it'll have more and more surface area, and the f functional is a weighted area. So if you have a variation that is too wobbly, then you will increase the area and increase the F functional, and therefore you're not going to be able to find a unstable variation that way. So a few more results on the index. So I was able to prove that the eigenvalue that numerically seemed to be -1 is actually -1. And actually, in the process of understanding why that is the case, I was able to obtain index bounds, including upper bounds, on the index of rotationally symmetric tori. As far as I know, there aren't actually any other results giving upper bounds on the index of self-shrinkers. There are, however, several other people who have work giving lower bounds for the index of self-shrinkers. So I mentioned the work of Liu, but there are also other people, including I think some giving talks at this workshop, that found lower bounds for the index of self-shrinkers.